Okay, so I suppose we'll get going. Today's gonna be a short day, which I'm sure everybody loves. There's the quiz, and there's just a couple things I want to talk about. Actually, wow, it's one page, so maybe it's way shorter than I thought. Nobody's gonna be that upset about that. So last class, we did an introduction to set theory. A lot of it is reminder from high school, especially talking about Venn diagrams and some of these operations. But I just want to talk about it so that we're all on the same page, because we will end up using it quite a lot, especially in linear algebra topics. Specifically, some of these sets and this notation here. So these are the natural numbers, the integers, the rational numbers, and the real numbers. So counting numbers, positive, negative numbers, fractions, real numbers. This symbol here means belongs to or in. So A, this symbol, capital A, means A is a member of the set A. This is intersection, so you can think of it as and. So it's what do these two things have in common? That's what the intersection is. So we have this Venn diagram too. A, B. So intersection is this piece here, right? Where they overlap. What do they have in common? And then the union is just dump it all together, right? It's just dump it into a single bag. Like that, right? So that would be the union. This symbol here means subset, contained in, also is another word for it. So something like this. This is a set A, this is a set B. We would say A is a subset of B, right? All the stuff in A sits inside of B, right? So if there were something in A, if it looked like this, I guess, there's like a 1 there or something, which is not in B, then this would not be true, right? And speaking of Venn diagrams, this is Venn diagrams, right? It's the circles where you fill stuff in. A lot of them that I will have you do will be filling in specific numbers, not shading stuff. But when we're talking about databases, hey, I relate to that. When we're talking about databases, you'll often shade in Venn diagrams to figure out joins. Well, not often. It's helpful, right? If you're more of a picture type person, a visual type person, then drawing these Venn diagrams to figure out your joins can be helpful. And so there is the quiz today, which it's going to be very much like what I had you do as like an exercise at the end of class yesterday. It's going to be filling in a Venn diagram and finding some intersections and unions and stuff. And then it's going to be talking about the Cartesian product, which we're going to introduce today. And assignment 1 is also due then. It's 3 questions. It's like quiz 1 and quiz 2 combined together with an extra one that I'll show you on the board how to play around with it. So with that said, I suppose we'll just jump into the topics, because like I said, it's probably not going to be a long one. It's going to be short. We have like a page, a couple things to talk about. So this is what we call a theorem, but we can just call it a result or whatever we want. It's how all of these operations kind of interact with each other, right? So suppose A, B, and C are sets. Then, so some of these are very similar to logic rules, but some of them kind of just make sense. I guess I could say it's in A. So what is this saying? It's saying if you take the intersection of two sets, then that sits inside of each of those sets, right? And that's pretty clear just looking at this diagram, right? The intersection of A and B is this middle part that I shaded like this. Well, that obviously sits inside of B, right? And also obviously sits inside of A, right? It's strictly inside of it. inside both of them, but it isn't each of them. That's all this is saying, right? This is sort of obvious from the Venn diagram. In fact, the proof of this is literally the Venn diagram, right? Sort of similar. Right? If you have the union, then each of those sets sits inside that union. Same exact argument through Venn diagrams, right? You've got A and B. The union is all of it. Well, if we take all of this picture, everything I just shaded in, then A is a part of that, right? So A sits inside of this picture. Similarly, B sits inside of that picture. So this makes sense, right? These are natural. We also have a distributive property. So A intersect with B union C, just like with logic rules, this sort of boils. And actually, the proof of this is just you look at the definition of what intersection and union are, and they're defined in terms of and or. So then you just say, essentially, by the rules of logic, this is true for logic, so it's true for sets. So there's not really a whole lot to be said there. Right, so it's just the outside operation becomes the inside one, and the inside operation becomes the outside one with the brackets, just like it did for logical operators. And the opposite is true with union on the outside. And then as a consequence of De Morgan's laws, if you try to take the complement of A intersect B, you flip the symbol, right? This is, again, ultimately because of De Morgan's laws, but you can kind of think of it in terms of Venn diagrams, right? So you've got this little shaded in region. Well, what sits outside of that? Well, the complement of A is this and also what's outside of it, right? And the complement of B is this and also everything outside, right? So this makes sense. Because what this is saying is take this black part, but then take everything outside of it. So that's what we just found, right? I mean, in these sets, because we're doing a union, we've got some duplicated stuff, right? We're taking the outside twice, but when we do that, that's fine because we just remove duplicates. And same exact thing here. Take the complement of this. You flip the symbol, right? And actually, there are a lot more set operations too. Like we have, you know, A union B is the same thing as B union A. The same thing with intersection. There's all kinds of stuff that we get these for free from logic, right? If you look at the list of rules from logic, you could just write down an equivalent rule here, right? And it's free. Okay, so again, these are just kind of helpful for simplifying things sometimes. Although the difference with sets versus logic is we have Venn diagrams, so they're a lot more visualizable than abstract logic. So, you know, in theory, it's nice that this is true, but in practice, we would just draw a Venn diagram if we really needed to, and then the properties here matter a little less because we can just directly draw it, right? This simplification is only useful in theoretical situations or like algebra and stuff like that. Whereas when we're actually working in applications, we would take a look at this and we would just draw that, right? Like we would just shade it in. Okay, so one thing I want to talk about is if little a and little b are two elements, we can form what's called an ordered pair. The programming word for this is tuple. We sometimes use that in math too, but it's usually in math, if we're talking about ordered pairs, we'll just call it an ordered pair. If we're talking about more than that, well, we might call it a tuple, but you know. So the important property of ordered pairs is the following. If you have two different ordered pairs and you say they're equal to each other, well, just think in terms of, you know, coordinates, right? In graphing from high school. When would these two be equal to each other? What would we need? Yeah. Yeah, exactly. Yeah, we need them to be equal component-wise. If and only if A is equal to C and B is equal to D. So the important part here is when we're calling it an ordered pair, so that means the order actually matters, right? There is a difference between A comma B and B comma A. They are not the same thing. So for ordered pairs, the order matters. So A comma B does not necessarily equal B comma A in general. In fact, sometimes it doesn't even make sense because, and this is true in math, although oftentimes the sets we're interested in are just numbers. But if you're talking about programming and you've got a tuple, then this first one might be an integer and this might be a string. So then swapping the order doesn't even make sense, right? Like, because the first part here is an integer and the second one is a string. So it doesn't make sense to swap them or compare them or anything like that. So that we formalize that in math too. We kind of capture a way where it's like, hey, it wouldn't make sense to swap them anyway if you just know the definition. So if A and B are sets, then the Cartesian product, which is just a big math word, Cartesian means the plane. Where this is your x-axis, that's your y-axis, that's Cartesian, right? That just, the Cartesian plane is that thing. So this is a similar idea. So the notation is AXB, A times B. And what does a set look like? Well, it's all the ordered pairs, A comma B, where this first element is an A and the second element is an B. So I'm going to use the notation. And actually, sometimes we get even lazier. So I said and here. We often just write comma, right? If you see a comma written in set notation, it just means and. Like, all of these conditions are true. So A is an element of the set A, and B is an element of the set B, which makes sense from how we've defined it. And now this doesn't even make sense, right? Because if we swap the order here, then B might not even be in the set A anyway, right? So then it wouldn't make sense at all to swap them. So let's look at an example. So if A is equal to R, S, and T, and B is equal to, give me a fruit. Okay. Give me another one. like strawberries. I mean, I like apples too, but. So if we want to form the Cartesian product of these two things, so this set, then we just have to think, what are all the ordered pairs we can make from these two things? So, again, these are ordered pairs. So this, we have our set A, and we have our set B. So the easiest way to do this is just say, all right, take something from A, take something from B, and just write out all of them. Right? So something from the first set, something from the second set. There's only so many ways we can do this. So let's do R strawberry. And then we've got S apple, S strawberry, T apple, and T strawberry. And we could think about, is that all of them? Well, this is a counting argument. How many choices do we have for the first one? 3. How many choices do we have for the second one? 2. So the number of choices is 3 times 2. Right? This is combinatorics. It's counting. We'll talk about combinatorics more, but it's just a counting argument, right? You just think, how many choices do I have for the first one? I multiply that with the number of choices for the second one. So there is, so I kind of indicated over there, but the one that you would be familiar with for this is, again, it's called the Cartesian plane, but it's just the normal XY plane. Called the Cartesian plane. So again, you got an x-axis, you got a y-axis. And then again, going back to it, so we can't swap the order here, and this is a good demonstrator of that, because if you did, say, this point here, which is 2, 1, then if we swap the order, it means something different, right? It'd be 1, 2. So these are not the same point, right? They aren't the same thing. So you can't just swap them around, even though both of these are real numbers, right? I mean, this is something we know intuitively. That's why we call it an ordered pair. In this case, it's just reflected about the line y equals x, but I mean, in this case, it doesn't even, there's no reflection or anything like that. If you swap this, apple isn't a member of that set, so just you can't. So we can also go higher than this. It's called 3D space. There's lots of names for it, but I mean, it's the one that you would know. It's take this, and now you have a z-axis, right? That's all it is. So there's something kind of interesting about computer graphics that I feel like I should mention, and it's not even that consistent. So like if you're interested in game development and you're doing 3D graphics, oh boy. We generally agree, everyone agrees, which way is X and which way is Y in 2D space, right? So if I also drew this and then have my marker sticking out, which one's X, which one's Y, and which one's Z? Yeah, that's what we think from like science. No. Generally speaking, this would be X, horizontal, left, right, and then they call this Z, up, down. When you're looking at the viewport, that's up and down, right? So from your perspective, this is the z-axis, right? It's like up, and so then this is the y-axis sticking towards you. It's and that's not even consistent. So like that's I think I don't remember which one does that. Unity maybe does that. Different game engines have different conventions for this, which some of them are more convenient for other things, but it makes you think. Hey, we decided this is X and this is Y. Does it matter? No, we just decided it and agreed upon it. So be careful of that. It can catch you off guard. As just a random note. But we have more convenient notations for these two that we often write. So we'll write r squared for this, r cubed for this, to indicate there's 3 dimensions, 2 dimensions. And then you can go higher, which is important for linear algebra, right? We say r to the n is n copies of r. And when you start talking about that, it's impossible to visualize unless you start talking about projections, because you're like, what does 4-dimensional space look like? Well, we know what it looks like because you can take a 4-dimensional object and project it into 3-dimensional space depending on which way it's rotated. A 4-dimensional cube is called a tesseract. And you can look on Wikipedia for a fun visualization of it, like rotating along a specific axis, and it looks really weird. But in linear algebra, we talk about a lot of higher dimensional things because they have geometry associated with them, but sometimes that's not what we're interested in anyway. We don't actually care about the underlying geometry, so we just talk about R5 because there are 5 components, right? Do they mean anything geometrically? No, who cares? But we can still talk about like a 5 tuple, right? Like just 5 components in a vector. And that's a bit more abstract. We'll talk about that, but you can. The obvious application of that is just arrays, right? They're not always 3-dimensional, obviously. So that's the idea. That's it. Short one. So just really quick, I want to just show you this website. I shouldn't have turned this off. Well, I mean, I guess I should have, because then it would have been shining in my face the whole time, which would be pretty bad. Yeah, but this is annoying. So. Hooray! I guess I have to do this now, huh? Okay, so this is, I just have you do this for the assignment. It's just like a silly little website to play around with logic gates. So you just drag and drop things to connect them. Up here selects which logic gate you want, but for our language, which logical operator you're using. So let's say we wanted to put a not in. So we click add node, and now we've got a not gate. And how do we connect these together? You just click the dots and drag them, right? It's pretty straightforward. Most people figure this out on their own, but like I feel like if I'm gonna have you play around with the website, I should at least just show you how to do it. So I just have you play around with this little thing and just see what I gave you a specific set of operations or something like that. And I'm like, hey, okay, the first one is true and the second one is false. What's your output? In this case, false. Now it's true, right? For false, then true. So it's just playing around with this. Originally, and maybe I'll make it part of the final project or something like that. I had people make what's called a half adder and then a full adder on this because you can actually add numbers using these logic gates. It's kind of messy. So I was like, that's a bit much. But I'm still thinking of doing it because it's kind of fun. It gives you an idea of how a computer's internals works, right? How addition is done is it's a string of, okay, it's more complicated than that now because we've modernized it. We found better ways to do it. But you string together a bunch of half adders to get full adders, and then that's how you add binary, is these logic gates. But anyway, I just wanted to show you that. And I think I mentioned it. Wolfram Alpha is also something that I encourage you to use as a tool, because sometimes maybe ChatGPT will give you the right answer, but there's no guarantee. It can be quite dicey at it, because large language models just troll the internet to find stuff. But this is pretty good. So if we want to say truth table for not P or Q implies not R and not S and Q, just string random stuff together. There we go. Boom! It just spits out the truth table. Right. Now, this is not going to shock you, but if you just put down from Wolfram Alpha your answer, I'm going to give you 0. I mean, that's not a shock, because what math class have you ever just been able to write the answer down in? I don't care what your answer is. I care about if you can understand what you're doing. But I want to show you the tool because it's very useful for checking your answers, right? If you, the typo on the homework assignment or the last quiz wouldn't have happened if I just typed it into Wolfram Alpha and checked, right? I would have been like, wow, that doesn't match what's on my sheet. I screwed up because this glorified calculator is way better than I am. So this is just an example of like one of the things it can do, but like it can do way more than that. Like you can integral from 0 to 1 of over, so whatever, right? Like there's an integral, right? And it just spits it out instantly. So it's a very useful tool. Well, okay, and this is a terrible example because this is an integral that even if you were extremely experienced with calculus, you'd be like, I can't do that, because that's the zeta function. Don't worry about it. The point is, it can do advanced stuff, right? Like it's not just a calculator. It can do all kinds of stuff. So again, just using the right tool for the right job. If you're like, oh, I'm a little stuck on this, like, how do I row reduce this matrix? Well, it'll do it for you, right? It'll check it, right? I don't remember the notation. I think it's 1, 2. It'll give you suggestions too. So when we talk about linear algebra, boom, there, it just told me. So like when you're checking your answer, you can do it like instantly and you'll know whether or not you're right, which is the real value of it, right? If you have the same thing as this does, you're probably right. I would say if you have the same thing, either you colossally messed up several times in a row to somehow get the correct answer anyway, or you just have the right answer. So yeah, it's just a helpful tool. So anyway, I just wanted to briefly talk about it, and say, yes, I encourage it. Use it all you want, but you still have to explain what you do. So if you want to sit there and waste hours of your life trying to get Wolfram Alpha to do all the steps for you, then I can't stop you. But I mean, why? It's probably faster to just do it. Yep. No, but I can post them. Yeah, I mean, oh, so that the logic gate simulator is in the assignment, so you can like click it there. But yeah, I mean, I have no problem. Like I can put Wolfram Alpha on the Blackboard, no problem with that. And that way everyone has it. So